Okay, so let's start our class. Once again, I remind you what we're gonna do for this week and the next week, right? This week, today, we're going to continue to talk about the gas law. And in the lab time, we're going to, we're doing the lab 50. Okay, today we're not doing lab, instead we're solving the calculation. And also, meanwhile, I'm going to talk about what exactly is a solutions stoichiometry, because today in the lab, when we try to solve the concentration of the sodium hydroxide, and we'll need to, based on the solution stoichiometry, and figure out the concentration of the sodium hydroxide. Okay, yeah, so this is the target for today. And on Thursday, we're going to finish the gas part. And then in the lab time, we're going to work on and just do the study guide, okay, the practice, okay. And then next Tuesday, we will have the exam. Okay, we will have the exam. Okay, so this is the plan for this week and the next week. Next Thursday, we'll continue finish the lab 50. And also, we're going to talk about the unit 4 content. Okay, yeah. So this is what we do in the next time. Okay, so first of all, let's just review what we learned. Okay, last time we talked about the gas. We talked about three different states, and why we have a gas, liquid, and a solid. What is the relationship between the intermolecular force and the kinetic energy of the molecules? Okay, molecule moving all the time. Okay, and the reason you have the solid, liquid, and the gas, that's because intermolecular force that compete with the kinetic energy. Okay, if you have a higher kinetic energy and less intermolecular force, then you're gonna have a gas. If you have the similar intermolecular force and the kinetic energy, you have a liquid. Okay, if the intermolecular force is overpower the kinetic energy, then you have a solids. Okay, so it's kind of like a trap at all the molecules together. Okay, so this is what we talk about. And we also talk about the gas, several gas law. Okay, we talk about the Boyle's law, and generally the gas law is talk about we have 4 different parameters to determine the gas. And what if we make 2 parameters as a constant parameter, which means we're not changing those the 2 parameters. And what is the relationship between the other 2? So that is the gas law talking about. For the Boyle's law, and they're having the temperature and the moles of gas as a constant. So then we're changing the pressure, and then what is the relationship between the volume and the pressure? So that is the Boyle's law. So we look at the video, and it says if you increase the pressure, and then the volume of the gas will decrease. If you decrease the volume of gas will increase. And you decrease the pressure, the volume will increase. So you can write either P times V is equal to a constant, or you can just write a P1 V1 equal to P2 V2. That's talk about 2 different points. If you have the one point shift to another point, and then based on the parameter, you can figure out the other point. Okay, so that is what we call the Boyle's law. Charles' law, we also talk about Charles' law. Charles' law is talk about if we have a pressure and moles of a gas as a constant, and what is the change when we change the temperature? What is the volume change when we change the temperature? And we saw the video, right? You put the balloon into the liquid nitrogen, then you will see a flake when you take the balloon out. Okay, so that means if you decrease the temperature, the volume of the gas will decrease. Increase the temperature, the volume of gas will also increase. So when you write the chemical, then if you write the equation, that's just V over T should be equal to a constant. I hope you can make put the name and the equation, you can link them together, okay? So what is the Boyle's law? Okay, what is the Charles law? What is the equation associated with? This is the things then you need to remember. And also you can write like a V1 over T1 equal to V2 over T2. Okay, so let's do one of the question. We didn't do the practice on the Charles law, but this one is what we need to talk about. Okay, so let's look at one of the questions on the study guide. This one is in the page 16. Okay, the page 16. Let's look at page 16. Okay. So this one is talk about calculate the decrease in temperature when 6 liter at 20 Celsius is compressed at a constant pressure to 4 liter. Okay, so we're talking about, okay, what is the temperature we need if we try to move the volume from 6 to 4. Okay, so now let's see. The first one, 6 liter, obviously that's a V1. And the second one, the liter, that's a V2. And this is a T1, and we're asking for T2. So we're asking for T2. But one of the important thing when we doing the gas law is Celsius cannot be used in the calculation. Okay, all the temperature have to convert to Kelvin. All the temperature have to convert to Kelvin. This is the most important thing, okay? All the temperature have to convert to Kelvin. So now you have a 20 Celsius. So if you're trying to convert to Kelvin, is the 20 plus 233, okay? So 233, that's a 20 plus 233, that's gonna be the Kelvin. So the first one is 20 Celsius. If you convert to the Kelvin, that's gonna be 293 Kelvin, okay? So you have to convert that to Kelvin before you're doing the calculations. If you're using Celsius, it doesn't work, okay? Have to be using the Kelvin. So now you have V1, you have V2, you have T1, and we're going to solve the T2. So let's set up the equation first. V1 over T1 should be equal to V2 over T2, okay? So now when you do this, you know we should go cross and try to figure out the T2. Now the T2 should be equal to T1 times V2 and divided by V1. T1 times V2 and divided by V1. You see? Now that's gonna be so that's why I recommend you to make a list of each of the parameters. So you know which one is P1, which one is V1, which one is V2, because you see the equation, the symbol is not always T1 times V1 divided by T2, okay? Yeah, so if you know which one is a V1, when you list those parameters, it's easy for you to replace those symbols with numbers, okay? Yeah. So now T1 is this one, 293. Then times T2, which is 4.00, divided by V1, which is 6.00. Okay, so now you can, based on this, to calculate 293 times 4 divided by 6, and you have 195.3. 195.3 and this is in Kelvin, not in Celsius. Okay, so if the question asking for Celsius, then what are you going to do? You have to convert back to the Celsius. Okay, the Kelvin always is a big number. So if you convert to Celsius, you have to subtract 273. Okay, so if you write 935, that's fine. But if you want to convert to Celsius, then you have to subtract 273. Okay, you have to subtract 273. You got Celsius. Okay, yeah. So that's really depends on what the question asking for. If the question asking for Kelvin, then your answer will be just Kelvin. If the question asking for the Celsius, then you have to subtract the 273 to get Celsius. Okay, yeah. So this is the sometimes is the part that you may got wrong in the questions. And look at what's the question asking for. Is it asking for the Celsius, for the temperature, or Kelvin? But doesn't matter what kind of units they are asking for. The answer, or when we do the calculation, we always using Kelvin. When we put it into the equation, we always using Kelvin. Okay, yeah. So let's we can do one more. So let's look at the question 10, and this one is a conceptual question. You see, there's no such numbers in this question, and let's see how do we solve this problem. So what will happen to the volume? They're asking volume when the temperature is doubled at a constant pressure. When the temperature is doubled at constant pressure. So now what do we know? Now we can just assume, okay, the first one, let's say we have V1, we have a T1. Second point is V2 and T2. So now what happens for the T2? The T2 is the temperature is doubled, which means the final temperature is 2 times of the initial temperature. That makes sense. Makes sense, right? So that's why the T2 should be equal to T1. And then let's see what they're asking for. They're asking for the volume, which means asking for the V2, because there's what happened to the volume, which means the second volume. What happened to the second volume? Is this changing? Is it getting bigger or decrease? Okay, so now they're asking for the V2. Then let's see what happened. So the V1 over T1 should be equal to V2 over T2. So V2 should be equal to V1 times T2 divided by T1. Well, we still can replace the stuff over there. V1, we still just write V1. And you got time T2. T2, that's equal to 2 of the T1 because the temperature is doubled. And then you're going to divide by T1. So now you will see what's the result. The result is 2 of the V1 because T1 and T1 is canceled. So now we got 2 of V1. So what happened for the volume? Volume is also doubled, right? Yeah. So this is that is why this is a relationship, right? We talk about increase the temperature, the volume will also increase. You increase 2 times of the temperature, you double the temperature, then the volume will also be doubled. So this is the relationship between the volume and the temperature. That is for Charles' law. Does it make sense, right? Yeah. So this is the Charles' law that we're talking about. Make sense, right? Okay. So this is the gas law for the Charles' law. Okay. And then we can let's look at the other laws. Today we'll continue to talk the other laws. Okay, so the next one we're going to talk about is the Gay-Lussac's law. Okay, the Gay-Lussac law is talk about if we have volume and the moles of gas is equal to a constant. So if the volume and the gas, moles of gas are constant, so you can think about how come we can make the volume and the gas, moles of gas as a constant. Well, then if you have so if you're using the high pressure cooker, then you probably know it, right? So if you have a metal container and the metal container, the volume will not going to change, okay? And the gas inside should be a constant number. So in the metal container, inside of metal container, and the gas inside should be have this kind of the parameter. We have a volume is fixed and moles of gas is fixed. Okay, so now here is talking about what is the relationship between the pressure and the temperature. Okay, so what is the relationship between the volume and the temperature? Okay, so what is the relationship between the pressure and the temperature? So you can think about it. Okay, so if we have a high pressure cooker, when the pressure go extremely high, what happened? It probably will explode. Okay, yeah. So that means if you increase the temperature, the pressure inside will also increase. Okay, so why? You can think about it, imagine that we talk about a molecule is moving all the time. Increase the temperature, the kinetic energy of the molecule will increase. So in another word, the molecule is keep continue heating on the wall. And then the pressure is going to getting faster and higher. Okay, so that is why. Okay, yeah. So gas molecule is going to increase the pressure. That's because the temperature increase make the kinetic energy of the molecule goes high. Okay, so that is the relationship. If you increase the temperature, obviously the pressure of the gas molecule will also increase. If you decrease the temperature, the pressure of the molecule will also go decrease. Okay, so this is normal. Oh, probably I didn't mention that. Did I mention how come the gas can make a pressure? Did I mention that? How come the gas can have a pressure? So generally, the reason the gas molecule has a pressure is because its gas is start to heating on the wall. Okay, different molecules is going to heating on the wall. One is heating on the wall, and then they will bounce back, right? So when they hit on the wall, they generate a force on the certain area, and the pressure is generated. Okay, so the reason, so we are exposed the pressure is because the air molecules, well, the air is constantly heating our body, so we generate the pressures. The reason we didn't feel any pressure is because you're already used to it. Okay, yeah, and also the inside pressure. You also inside you have pressure, the outside also have pressure. Those two pressures equal to each other, so you didn't feel anything. But what if you're suddenly be transported in the outside of the out space? Then what happened? You're gonna explode. Okay, yeah, so you're gonna explode because the inner pressure is much stronger than the out pressure. There's no out pressure when you go outside space. So everything inside will be exploded. Yeah, that's for sure. Okay, yeah. Okay, so there's the relationship. Then if you want to write this, you can write like a P divided by T will be a constant. Pressure over temperature will be a constant. Pressure over temperature will be constant. Or if you have a 2 point, you can also write like a P1 divided by T1 should be equal to P2 divided by T2. So this is called the Gay-Lussac law. Okay, this is called the Gay-Lussac law. Okay, so that is the relationship talking about the pressure and the temperature. Okay, relationship between pressure and the temperature. Okay, we can do one of the practice still in page 16. Let's just look at the first equation. So here it says the gas in a hairspray can are at a temperature 27 Celsius and a pressure of 30 psi, this pound per square inch. If the gases in the can reach a pressure of 90 psi, the can will explode. So here it said, to what temperature must the gas be raised in order for the can to explode? Okay, yeah. So that means the final pressure need to reach to 90 psi. Initial is 30. So initial temperature is 27 Celsius and asking for what is the final temperature. Okay, so again, I recommend you do this to make a list for each of the parameter. So first one, we have a temperature which is 27 Celsius. And again, we have to convert the Celsius to Kelvin before you're doing the calculation. You plus 273, and you know this is 300 Kelvin. Okay, then we have a P1. The P1 is 30 psi. Okay, so when you do the gas law, it's not talking about for the pressure and the volume is not required what kind of unit you have to be formed, but the temperature have to be 300, have to be in Kelvin. But for the pressure, if the both pressure are the same unit, then that's okay. So the P2 will be 90 psi, pound per square inch. And then they're asking for what is T2. So P1 divided by T1 equal to P2 divided by T2. Okay, so now you see the T2 should be equal to P2 times T1 and divided by P1. So now you can go ahead to replace those parameters. Now 90 psi times 300 K and divide by 30 psi. And then you can easily figure out this is a 900 Kelvin. If the question asking for what is the Celsius, okay, what is the temperature in Celsius, must the gas be raised in order for the can got explode? Then you have to subtract the 273 to get the 600. So the Celsius will be just the 900 K subtracted to 73 K. Then you got 627 Celsius. Okay, yeah. So this is the temperature. So when we do the calculation for the temperature, have to using the Kelvin. Okay, have to using the Kelvin. All right. So this is talking about the Gay-Lussac law, or also called the Emerton's law. Okay, Emerton's law. Okay, so the next one we're going to talk about the next gas law, which is called the combined gas law. So the combined gas law actually is just a combine the previous three gas law together. Okay, the first one, the Boyle's law, is talking about the P times V equal to a constant. And the second, the Charles law, is talking about V over T is a constant. The last one is the Emerton's law. It's talking about pressure over T is a constant. So those three are constant. So once you combine those three equations together, you will find the P times V over T. That's gonna be a constant. P times V over T, that's gonna be a constant. So as long as the moles of gas is a constant, if the moles of gas are a constant, then the relationship between those three parameters is this. The pressure times volume divided by temperature will be a constant. Okay, so that is the relationship between those three parameters, and this is called a combined gas law. This is called a combined gas law. Okay, yeah, combined gas law. So if you have a 2 points, you can also write like a P1 times V1 divided by T1. That should be equal to P2 divided by V2 and time V2 divided by T2. And this is the relationship. Okay, so the previous three laws and only have 4 parameters, but this guy has 6 parameters. Okay, they have 6 parameters. Okay, so this is called a combined gas law, and we can do one of the examples also in our study guide. So let's look at the first question. First question in the page 17. A gas balloon has a volume of 106 liter when the temperature is 45 Celsius and the pressure is that much mercury millimeter height of mercury. So what will its volume be at 20 Celsius and 780 millimeter height of mercury? Okay, so now, so this is why, okay, since the parameter is getting more and more, and things getting more and more, and then we have several laws, gas laws shows up here. I'm sure you know each of this equation, you know how to solve it. But the problem is, in the questions, I don't know which one we're going to use, right? Yeah, I don't know which equation I'm going to use. There's a lot of equations we probably can use, but when I raise these questions, what kind of equation do I need to use? That's gonna be a problem. Okay, yeah, that makes sense, right? Yeah. So that is why I recommend you put the list of the parameters out. Okay, yeah. For example, if the parameter only just give your T temperature and the pressure and nothing else, what equation you're gonna use? Obviously, you can only use in the equation that containing pressure and temperature, right? So if I give you the equation, the parameter only just give you the volume and the temperature, then what are you gonna do? Obviously, you can only use in the equation containing the volume and the temperature. That makes sense, right? So that is why if you list the parameters out, it's pretty straightforward, showing you what kind of equation you're gonna use. That makes sense, right? Okay, so let's look at this. Is this true? Okay, so the first they give us a volume, and then they're asking for another volume, right? They're asking for another volume. So the first one obviously is a V1. That's a 106.0 liter. And then they give you also 2 different temperature, right? So one is 45 Celsius, the other is 20. So the T1 should be 45.0 Celsius, and you're gonna plus 273 to got the pressure, to got the Kelvin. And this is 318 Kelvin. And also you have the other, you have another pressure. We have 2 different pressure. The first pressure is 740.0 milliliter height of mercury. And the second pressure is 780.0 millimeter height of mercury. And the T2 is 20.0 Celsius plus 273 and got 293 Kelvin. Okay, so now you see the question asking for another volume, which is V2. So now what we have? We have five of the parameters shown, asking for another one. So obviously, this one is using combined gas law because combined gas law has 6 parameters and having volume, temperature, and the pressure. Okay, so that is why you're going to using the combined gas law to solve the problem. Okay, so now P1 V1 divided by T1 should be equal to P2 V2 and divided by T2. Well, this one is a little bit complicated. And the question asking for V2, so the V2 should be equal to, again, that's 1 times this divided by the rest of the T1 V1 times T2 and divided by T1 and time P2. Okay, so this is the equation. And another beauty of making the list is, well, you can easily to replace the symbol with numbers. Okay, you won't mess up when you do the calculations. Okay, yeah. So the P1 is 740. A time V1 is 106.0, and a time T2, which is 293, and divided by T1, 318, and time P2, 780. Okay, when you do the calculation, make sure the bottom part has a parenthesis. Okay, 740 times 106.0 times 293 divided by parentheses 318 times 780 parentheses. Answer will be 92.6 or 92.7. Okay. 92.7, and this is in liter. Okay, so what kind of unit you're going to use? That really depends on what's the unit for the previous volume. If the previous volume is in milliliter, then the unit is going to be milliliter. If the previous is liter, then the second unit will also be the liter. Okay, so this is how we solve this kind of the combined gas law. Combined gas law. Any questions? Okay, yeah, to be honest, this equation is not that hard. Hard is what kind of equation you're going to use when you do the calculation. Okay, so let's take a break. Okay, let's take a break. Okay, so let's come back. The next one, is the last gas law we're going to talk about, and this is called Avogadro's law. Avogadro's law. Okay, and this Avogadro is the same Avogadro we talked about for the moles. Okay, 6.02 times 10 to the 23rd. Avogadro's number, the same person. Okay, Avogadro's law actually is talking about if the pressure and the temperature are constant. If the pressure and the temperature are constant, what is the relationship between moles of gas and the volume? Okay, what is the relationship between gas, moles of gas and the volume? Well, so pressure and temperature be constant is pretty easy to be controlled. The current temperature and the volume, temperature and the pressure is constant. Okay, yeah. So as long as if we have the circular system, that should be, constant. So, what is the relationship between those two? And you can think about it. Okay, so one day somebody got a birthday, and you will want to go to the Dollar Tree to buy the balloon. Okay, yeah. So you buy several balloons, and what is that called? The cashier and helping you to purge the helium gas into the balloon. Once you purge the helium gas, actually you're increase the moles of a gas, right? Makes sense, right? Yeah. So the more gas you purge in the balloon, the bigger size the balloon will be. That makes sense, right? Yeah. So that is just a relationship between the moles of gas and the volume. If you increase the gas molecules, then obviously the volume will increase, right? Because it's expanding, okay? So that is the relationship. If you increase the moles of a gas, the volume of the gas will increase. If you decrease the volume, the moles of gas, the volume will also decrease. Just like the balloon is getting leaked, okay? Then the balloon is shrinking, right? Yeah, that's normal. So that's just a reason, okay? Yeah, that's remind me. Yesterday, I bring my daughter to the trunk or treat activity, and they have the balloon artist. You know, the balloon artist out there making different things like a sword, the bunny, and the dog, right? The puppy dog and the flower, a lot of things. So they both of them making the bunnies. I know. Eventually it will leak. It will shrimped. Okay, yeah. So that's just a leaking things. Okay, once you're leaking, the volume of the gas will decrease eventually. Okay, so that is the relationship. When you set up the equation, and you can see that actually just the volume over the moles of gas, that should be equal to a constant. Volume versus moles of gas, that's equal to a constant. Or you can see V1 over N1, that should be equal to V2 over N2. So that is also the relationship between the Avogadro's law. Okay, I know this one, and if you see, this one is the only one that changing the moles of gas. Okay, for the previous other four laws, the moles of gas are all constant, but this is only Avogadro, only gas law that changing the moles of gas. That makes sense, right? Okay, yeah. I'm not going to using this. Okay, there's another parameters or knowledge that associated with the Avogadro's law, And we're going to, this is not a very important part, but the next concept related to this is more important, okay? So the next concept we're going to talk about is called molar volume. Molar volume and STP. Okay, molar volume and STP. So first, let's talk about what is STP. Okay, so this STP means standard temperature and pressure. Okay, STP, that means standard temperature and pressure. Okay, so this standard temperature and pressure is different from the standard temperature, standard condition in the chemistry, in thermal chemistry. Okay, so here, this is STP, the standard temperature and the pressure is different from the thermal chemistry standard conditions. Okay, so here, this STP, the pressure is still the same, is 1 atmosphere. I still talk about 1 atmosphere. But for the gas, in the gas law, the STP here, the temperature is not 25 Celsius. This one is 0 Celsius. It's 0 Celsius or it's 273 Kelvin. Okay, so that is the huge difference between the standard STP and the standard condition in the thermal chemistry. Okay, yeah. So we using this STP more often. So you're probably gonna remember this, okay? 0 Celsius or 273 Kelvin. Okay, that is the standard STP. What does the STP mean? 0 Celsius or 273 Kelvin, okay, 273 Kelvin and 1 atmosphere. So what is the molar volume? Molar volume is just the 1 mole of gas, the volume, molar volume, that means the volume of 1 mole of gas, 1 mole of any gas. Okay, the volume of 1 mole of any gas at STP. Okay, so that means the condition under the STP condition, okay, 1 mole of gas, what is the volume of 1 mole of gas? Okay, the volume of 1 mole of any gas at STP condition. Okay, so this is what we call the molar gas or molar volume. And this number is a fixed number. Okay, this number is a fixed number. It doesn't matter what kind of gas. Could be oxygen, could be CO2, could be carbon monoxide, could be hydrogen, any of that. Okay, doesn't matter what kind of gases. As long as it's a gas, the volume of the 1 mole of this gas at STP condition is a fixed number, which is 22.4 liter per mole. Okay, 22.4 liter per 1 mole of this gas. 1 mole of this gas is 22.4 liter. Okay, well, then you can think about 2 moles of this gases. That's going to be 44.8 liter. Okay, it can be doubled. Okay, so this volume is really just related to the moles of gas. Okay, you have much more moles of gas, you're gonna have more volume. Okay, as long as it's under the STP condition, the volume will be just like this. 1 mole of the gas is equal to 22.4 liter. This is a fixed. It really doesn't matter what kind of gases. Okay, really doesn't matter what kind of gases. Okay, so this is what we talk about for the molar volume and STP. Molar volume, the molar means 1 mole. Okay, molar volume is a volume of the 1 mole of any gas at STP condition, and this number is 22.4 liter. Okay, 22.4 liter. The reason I'm writing per mole, that means just 1 mole of this gas is 22.4 liter. Okay. So let's work on some of the practice. Then you can look at the first one. First one is that 50 gram of the nitrogen has a volume of how many liter at STP condition? Well, so what do we do? First, we know we talk about moles of gas. We're not talking about mass of the gas, right? So first of all, you have to convert the mass of the nitrogen to the moles of the nitrogen first. Okay, yeah. So remember, the molar mass of the NO is 28 gram per mole. It's not the 14, okay? It has 2 of nitrogen. So first, we figure out the moles. The moles of the nitrogen here is just a 50 gram divided by 28 gram per mole. Mass over molar mass, 50 divided by 28, 1.786. 1.786 moles. Okay, and we got the moles of this, and we try to figure out what is the volume at STP. Now you have 2 different ways to solve the problem. Okay, we can based on the Avogadro's law to solve this problem, or we can just using the 22.4 liter per mole at STP condition, right? Yeah. So, so if you're using the Avogadro's law, then you know the condition. Well, we know the volume V1 over N1 equal to V2 over N2, right? So you can see what is the relation. The V1, V2, you can see this is a 22.4 liter per 1 mole of the gas. And then the V2, what is the V2? And you're looking for this. The V2 versus the moles of gas, 1.786 moles of gas should be equal to 22.4 liter over 1 moles of the gas. That makes sense, right? Volume over mole should be this volume over mole. That makes sense, right? Yeah. So in this case, you can solve the V1 will be just 22.4 liter times 1.786 moles and divided by 1 mole. And then you will see 22.4 times 1.786 and 40. Then that's a 40. Okay. So that's a 40 gram. Sorry, 40 liter. Okay, that's going to be 40 liter. Okay, so you can, this is one way to solve the problem. The other way, you can also using the, 22.4 liter per 1 mole. Okay, yeah. So this guy, we have this relationship, which means 1 moles of the gas is equal to 22.4 liter, but this is under STP condition. So very, very important. The reason we can using that is because the question is already said this is a STP condition. But if the question not saying this is STP condition, then you cannot using this equation. That makes sense, right? Yeah. So now you know 22.4 liters should be equal to 1 moles. Now, how many moles do we have? We have 1.786 moles of gas. And then you're going to convert this 1 moles of the gas equal to 22.74 liter. So moles of gas, moles canceled, you still got 40 liters. Okay, the same thing. Okay, it doesn't matter which one you choose, you can do the same thing to solve this problem. Make sense, right? Okay, yeah. So this is a talk about the Avogadro's law. Okay, next time, Thursday, we will do some practice on this part. Okay, yeah, we will keep continuing. And also, again, if you're not interesting, if you want to get better in the exam, better to work on the more the better. Okay, yeah, work on those, the more the better. All right, so let's take a break again, and then we will talk about the other one. It's called the ideal gas law. Okay, ideal gas law. Okay, so let's come back. The next one we're going to talk about is called the ideal gas law. Ideal gas law. Okay, so last time we talked about why this is called an ideal gas. Okay, and we talk about what's the difference between ideal gas and the actual gas, right? And last time we talked about what is the ideal gas versus the actual gas, but I try to remind you what is the difference. Okay, ideal gas and is the gas we talk about. I mean, the gas molecules is pretty far away from each other's, so there's no interaction, or the intermolecular force is really minor or very negligible. Okay. Compared to the space. So the molecules, the two molecules, there's no interaction between each others. Okay, so this is called the ideal gas, which means the space of the gas is big enough. So there's no interaction between the molecules. But for actual gas, That means in some of condition, the gas, they do have the interaction between each others. If your things happened in a very small chambers, okay? So if you have a very high pressure, you press the molecules in a really, really small chamber, then the molecule itself, they do have the interaction between each others, okay? Like the gas molecules, that is compressed inside of the car's engine. Okay, car's engine. They gonna have a really, really high pressure inside of the engine. So in this case, they do have the interaction. The molecule and the molecule has a really, really narrow space between each others. So the intermolecular force between each other will have a much more effect on the ideal gas. Okay, so that is why the ideal gas law in that case is not suitable. Is not suitable. Okay, yeah. So when we talk about the ideal gas law, this law, the relationship between those is talk about ideal gas, but it's not used to. It's not suitable for actual gas. Okay, the actual gas has another effect, will affect the actual gas. So we're only talking about ideal gas in this case. The ideal gas law, this one actually is coming from the previous gas law. If you combine those 5 laws all together, actually is just an ideal gas law. Okay, nothing special. But in this case, is combine everything together is P times V equal to N times R times T. So this is the relationship between the ideal gas law. This is the relationship between the ideal gas law. So if you convert this a little bit, you will see PV times N divided by T. That should be a constant. Should be a constant. Again, so let's just say a little bit. We talk about the first one is the Boyle's law. Boyle's law is P times V equal to a constant, right? The second one is Charles' law, V over T equal to a constant. The last one, the next one is the Hamilton's law, is P over T equal to a constant. And then the last one is Avogadro's law, is a V over N equal to a constant. You see, if you combine them together, it's just exactly just like the P times V equal divided by N T equal to a constant. You see, N is in the bottom, T is on the bottom, P and V on top. So that is, if you combine them together, will be got this. And then the people figure out what is the constant over here. And this constant is just the R. And this R is what we talk about, is called the ideal gas constant. This R is called the ideal gas constant. So we make this equation like this. Yeah, we make the equation like this, PV equal to nRT. And the P, we know pressure, V is a volume, N is a moles of gas, T is the temperature, R is the ideal gas constant. Okay, we haven't talked about ideal gas constant, but based on the previous equation, you know, okay, R is a constant, and what is the value of this constant? Okay, the value of the R, if you search online, there's a lot. Ideal gas constant, there's a lot ideal gas constant. You see, those are all R, 8.314. 0.08205. Those are all ideal gas constant, okay? And those are all the ideal gas constant. But how come when we figure out the constant, but the constant are different number? That is because they have a different unit, okay? Once they're using different unit, and then we're going to get having the different constant, okay? If we have a different unit, we're going to have a different constant. So that is why in here, the ideal gas constant, here, the constant we're using is 0.08206. Okay, 0.08206. And the unit, remember, the unit is atmosphere time liter divided by Kelvin and divided by mole. Okay, so that is the unit we're using. Okay, and so that means when you're using this equation, PV time NIT, then you have to stick with the unit over there. Otherwise, you cannot use the constant here. Okay, yeah. So that's why the pressure, you have to using atmosphere for the pressure. Okay, and you have using liter as for the volume. For the moles of gas, you have to using mole, and temperature have to using Kelvin as a unit. Okay, so this is very important to using the ideal gas law before using the number before you put in this. Okay, if you want to using the R constant 0.08206, then you have to using the number, the unit like this. Otherwise, you cannot using this constant. The constant, the number will change. Okay, the constant number will change. Are you clear? Okay, yeah. So PV equal to nRT. Okay, again, the question are pretty similar. Okay, and if you know, okay, how come I know we're going to using this constant, this ideal gas law, not the other gas law? Well, that's because the question will give you those parameters. So the only suitable equation is ideal gas law. Then you have to using this equation to solve the problem. Okay, so let's turn to the page 17. I think it's 17. 17 or 18. Okay, so let's look at the first question. This 18, page 18. Let's look at this question. So the ideal gas law is talk about for the first one, a tank containing the moles of gas, 115 moles of the neon gas. It has a pressure, and they shows the temperature. They asking for the volume, right? So when you make the list of this, you know that N is 115 moles of gas. The pressure is 57 atmosphere, and the temperature is 45 Celsius. Again, you're gonna convert that to a Kelvin. Then you got 318. This is Kelvin. And then the question asking for the volume. You see, this is what the parameter telling you. The parameter give you this moles of gas, pressure, and temperature, asking for volume. Based on the previous those equations, the only equation that we can use is ideal gas law, PV equal to nRT. In that case, we know 4 parameters, right? PV equal to nRT. There's a 4 parameters shows up there. If we know 3 of them, we should be able to solve the 4th one, right? So this is the only equation that we can solve this problem. So that is why you're going to using the ideal gas law equation. So we're asking for V. So the volume will be just equal to the nRT over the pressure. Okay, nRT over the pressure. So you can plug those numbers in there. 115 times R, which is 0.08206, and time the temperature, 318, and divided by the pressure. The pressure is 57 atmosphere. Okay, so now you can put this in the equation. (115) times 0.08206 times 318 divided by 57. So we got a 52.6. Okay, 52.6. 52.6. Okay, 52.6, and this is in volume, so that should be in liter. Okay, the answer should be, I think the answer should be 53 liter, because you see, if you look at the numbers shown here, there's the smallest is 2 sig. So we should keep a 2 sig. It's not a 52.67. Okay, yeah. Well, so this is ideal gas law, right? This is give you this examples. Well, then let's go back. Let's go back to talk about, okay, so last time we talked about 22.4 liter per mole, right? We call this is a molar volume for the gas. Molar volume at gas, they have a condition is at STP condition. Well, let's see. How come we can figure out it's 22.4 liter? Well, this is actually, this number is being calculated by using the ideal gas law. Remember, so in this condition, what do we have? So we know the moles of gas here is 1 mole, right? We talk about 1 mole of gas is how many volume. So let's see whether we can, based on the ideal gas law, PV equal to nRT, to figure out the volume of the gases. Okay, now the moles of gas is 1 mole. And again, what is the temperature in this STP condition? What is the temperature for the STP condition? 0 Celsius. So that's a 273 Kelvin. That's a 273 Kelvin. And what is the pressure under the STP? 1 atmosphere. So now we're looking for what is the volume for this. Let's see. Okay, so PV equal to nRT, the volume will be just the nRT divided by P. Okay, so now 1 moles of gas time 0.08206, and your time temperature, which is 273 Kelvin, divided by pressure. So we put everything into the calculator. 1 times 0.08206 times 273 divided by 1. What we have? We have a 22.4 liter. Okay, 22.4 liter. So that is why 22.4 liter. Okay, so this number also can be calculated based on the ideal gas law. And this is where those numbers coming out. Okay, if we have 1 moles of gas under 1 pressure atmosphere, and the temperature is at 273 Kelvin, and the volume must be 22.4 liter. Okay, no other number can be calculated because the gas is controlled by those 4 parameters we talk about, right? So if the 3 parameters are fixed, the other one should be fixed. Okay, so that is the relationship between the gas P, pressure, volume, moles of gas, and the temperature. Those 4 are related to each other's. Okay, if 3 parameters are fixed, the other parameter should be fixed. Okay, then it should not be changed. Okay, and this is the ideal gas law. Okay, this is the ideal gas law. Okay, so for the ideal gas law, they have another variation for the ideal gas law. So we have like 10 minutes. So we're going to use the 10 minutes to talk about another variation for the ideal gas law. Now, what is a variation? You can, based on this question, you see. So look at this question number 5. Here is that we have a 23.6 gram of the unknown samples. And this sample occupies a volume of 12.0 liter at a standard temperature and the pressure. So asking for what is the molar mass of this gas? What is the molar mass of this gas? Ideal gas law, PV equal to nRT. It's not talking about, okay, so now here we have a volume. Now we got it. Yeah. We have the standard temperature and the pressure. So we got the temperature and the pressure. Yeah, but the point is we're not having the molar mass. Well, we still can solve the problem because we got a mass over here. Well, this one is not. Okay, let's look at the other one over here. Okay. Okay, so let's look at the question number 9. Here it said a certain gas has the density of that. And we have the temperature and we have a pressure asking for what is the molar mass of these gases. Well, P times V equal to nRT. There's no density shows over here, right? There's no molar mass shows over here. How come we can using the ideal gas law to solve this problem? Okay, yeah. So this is why we're talking about the variation of this ideal gas law. The variation of this is the pressure times the molar mass of the gas should be all equal to the density times R times T. Okay, the mu here is the molar mass of the gas, and the rho here is the density of the gas. The density of the same gas. Okay, so this is the variation. So let's just talk about how come we have this equation, and this equation also called the ideal gas law. An ideal gas law. Okay, so this equation actually is coming from the PV equal to nRT. T. This equation is coming from the PV equal to nRT. So what do we do? First of all, we divide by V, the volume on both sides. So you will see that's going to be a pressure that should be equal to N divided by volume time R time T. Okay, yeah. So this is going to be the volume. Okay, the next part is we're going to multiply the molar mass on both sides. So the P times the molar mass of the gas, that should be equal to the mole times molar mass of the gas divided by volume times R times T. Okay, so now when we write like this, you can see mole times molar mass equal to what? Do you still remember the equation? Mole times molar mass equal to mass. Okay, mole equal to mass over molar mass. Molar mass times mole equal to mass. So mole times molar mass equal to mass, which is N times the molar mass. Those two times together actually is a mass. So you will see actually is a pressure times the molar mass of gas should be equal to the mass of the gas over volume of the gas times R times T. And again, what is the mass over V? More mass over V, that's a volume, right? That's a density. Mass over volume, that's a density, right? So that is why the pressure times molar mass of the gas should be equal to the density times R times T. Okay, so that is why we have a new equation. And this new equation is related to the molar mass of the gas and the density of the gas. Okay, it's related to the molar mass of gas and the density of the gas. Okay, so to be honest, at the very beginning, I have no idea why we need to have such equations. Why we're just using the PV equal to nRT. This one looks good. Why are we using this? Well, okay, until I teaching the classes, and then I realized, yeah, this is a good variation. Why? That's because, okay, the moles of gas is really mean nothing to us. Okay, yeah, you can figure out the pressure of gas, moles, volume of gas, and the temperature of gas, and you figure out the moles of a gas. Doesn't really mean anything to us, especially when you find some of the unknowns. You find some unknown, telling you, okay, the moles of this unknown gas is something. Mean nothing. I still don't know what is unknown, right? Yeah, but what if we convert that? We got the density of the gas is easy to find. We can figure out the mass of the gas, and we can figure out the volume of the gas. And then we can figure out the molar mass of gas. Well, once you know the molar mass of gas, then they give you some hint, because different parameter, the chemicals will have a different molar mass, right? If you know some molar mass of the gases, you can narrow down what kind of unknown gas it is. Does it make sense, right? Yeah, especially for those common gases. And then you can just, based on the molar mass of gases, you figure out what kind of unknown it is, right? So that is why this equation actually is more useful than these equations. Okay, especially in the lab. I mean, if you want to detect what kind of unknown it is, you're testing what kind of unknown for these gases. This equation is more useful than the first equations. Okay, because you can easily to figure out what is the molar mass of these gases, and then can easily to determine what kind of unknowns. That makes sense, right? Yeah. All right, so let's just go back to look at this equation again. Now we have the PV equal to nRT, then we convert that to P times the molar mass of a gas equal to the density of the gas times R times T. So now you have the density of the gas. So this is a density 2.23 gram per liter. Okay, we have a temperature. The temperature is 273 Kelvin. The pressure you have to convert to the atmosphere, not 760 millimeter height of mercury. Okay, and we talk about 1 atmosphere is equal to 760 millimeter height of mercury. So this is equal to 1 atmosphere. Okay, if you're still cannot remember what is the relationship between the millimeter height of mercury and atmosphere, you're gonna write this in the cheat sheet. Okay, yeah. And by the way, I probably didn't mention that the cheat sheet can be used in the following exam, but not for the final exam. Okay, the final exam is only just a periodic table and some parameters that shows in the ACS exam. Okay, yeah, you cannot use the cheat sheet for the final exam. Okay, yeah. So then they're asking for what is the molar mass. Okay, yeah. So if you look at here, the molar mass of the gas should be equal to density times R times T and divided by the pressure. Again, we're still can using the density here, 2.23 gram per liter times 0.08206 and the time temperature 273 divided by pressure, which is 1 atmosphere. And then you can figure out what is the molar mass of the gases. 2.23 times 0.08206 times 273 divided by 1. And we got 49.95. Okay, 49.95, which is 50. 49.95 is gram per mole. It's gram per mole. Okay, 49.95 gram per mole. Okay, so this is the molar mass of the gases. This is the molar mass of the gases. Okay, yeah. So generally, this is pretty much we talk about for today. I know today we talk about a lot of laws, right? And variations of laws, ideal gas laws. Okay, but the equation, as long as you know the equation, you should be able to solve the problem. Okay, yeah. Next time we will do some practice on those gas laws. Okay, we will do some practice on the gas laws. And next one in the lecture, we will continue talk about the gas law, how to using the ideal gas law to solve the problems. Okay, how to using the ideal gas law equation to solve the problem. All right, so let's end of this class and move to the lab.